Okay, I'm starting the recording. Let's wait till, I think it's recording now. Okay, let's just assume it's recording. See, it says recording. All right, everybody. Thank you for joining. Thanks for logging on. Today, we're lucky enough to have Mangpo talking to us. She's coming from Google, where she's heading the machine learning for machine learning compilers moonshot. I was lucky enough to work with Mangpo this summer on ML for ML compilers. She has a lot of really insightful work, and I'm really excited to hear what she's going to be talking to us about today. So with that, oh, and I should also say, Mangpo is a former member of Pulse. She was a visiting student. Should I say, is it visiting student from Berkeley? I'm not sure exactly what the exact definition is, but either way,
I think that would work. Yeah.
Mangpo was my original office mate. What's that?
There's no such thing as a former member of Pulse. She's a Pulse alum.
There you go, Pulse alum. Pulse alum. And Mangpo was my first office mate, and that's the whole reason. I mean, that's definitely a part of the reason I'm in Pulse, and the whole reason I was at Google this summer. So, with that, go ahead, Mangpo, take it away. And thanks for joining us.
All right. Thank you. Thank you for having me today. And yeah, I'll be talking about the work that I've been doing at Google for a few years now, and it's part of the machine learning for machine learning efforts at Google. And yeah, and feel free to interrupt me at any point in time when you have questions. And we have about an hour, right, until 1 p.m.
Yep. Yeah, we're till 1 p.m. So take, okay. I would say take as much time as you want. Leave some space for questions if you want, but if you want to take the full hour, also go ahead.
Okay, I'll try to leave some time for question. Okay, so yeah, so actually, so I'm gonna talk about auto-tuning production machine learning compilers. And of course, this idea of applying auto-tuning or search-based approach to compiling machine learning workloads are not new, right? We have seen in the past few years that there are this explosion of research in this space. Many of the work coming from, the group from UW and Pulse and SAMPL. So I want to categorize why we are different from existing works. So if you look at the majority of prior works, they are focusing on optimizing various kind of optimizations together, including loop tiling, loop fusion, vectorization, parallelization, and so on, right? But because of the richness of the search space, they can only focusing on optimizing for a subgraph, which contain only a few high-level tensor operations at a time. And there are some caveat at looking at search at the subgraph level, because the solution can be suboptimal. Essentially, a common strategy that most of the framework use to partition graph into subgraph is according to the neural network layers, right? And then essentially ignoring the cross-layer optimization opportunities, because this is how you scale the problem. Now, so we have an empirical experiment that we essentially disable the fusion opportunity across the layer by modifying the XLA TPU compiler to limit the fusion to be only within layers. And we observe a regression or slowdown of up to 2.6 times and 32% on average when we do this. So it's a huge performance loss. So then there are some research frameworks that apply search at the graph level, right? But because the graph is so much bigger than subgraph, they are only looking at limited kinds of optimizations in the search space. And despite the scope of the optimization, all these frameworks share the same caveat that it takes very long time to compile, right? Like when you have to apply search, this can take minutes to hours to just compile a model like ResNet inference. And if you compare this to a heuristic-based compiler like XLA, this takes seconds, right? And this is still the reason why production compilers still rely on traditional ways of building compiler by decomposing compilation problem into multiple passes and use heuristic to solve each of the passes for scalability, right? And this is because production compiler have to be able to handle industrial scale model that can be extremely large, containing up to 500,000 nodes. I have seen this in production. And or like some graph require that the end-to-end training time, including compilation, have to be finished within seconds. For example, like we have seen like ResNet training finished within a few seconds, right? So unfortunately, none of the existing approach that do auto-tuning or search can support auto-tuning different optimizations in this multi-pass style compiler. And the challenge is that the search space it's dynamic, right? When you look at a search space of a particular pass, it is highly dependent on decisions that have already made in prior passes. Or in another word, when you make one decision right now, it also affects the decisions in the future. It can disable or enable the decisions in later passes of the compiler, right? So this is the challenge that we have to tackle. So in
Can I
my
ask a question?
project, yeah, of course.
So in compiler, right? Usually, it looks like most people prefer the compiler's optimization to be modular. So it's kind of like more toward the subgraph approach rather than the graph approach. So can you compare and contrast why in your work or rather like in ML, like it's more preferable to have the whole program optimization rather than the modular approach, which I mean looks like bring a lot of benefit in the compiler fields.
I think there are different aspects of modularity, right? So there are modular in terms of the scope of program that you optimize for, right? So in C++, you can analogy to C++, the subgraph is basically like a function, right? But there are some optimization that you have to do it globally to enable more optimization. Like in C++, for example, there are some basic blocks like inter-function optimization that you can do, right? So similar here, there are also optimization at the whole program or the graph level that you can do. And there's actually a different angle of modularity because even though you solve the whole program optimization, you don't solve all kinds of optimization together. And in the compiler passes that we have, they actually modularize different types of optimization. So one compiler pass handle one kind of modular optimization problem. Yeah. So does that answer your question?
Yep. Thanks.
Okay. And then I'll go into a little bit more on like what kind of graph optimization problem that we do. Yeah. Okay. So, right. So the goal of our project is to then bring the benefit of this search-based exploration to multi-pass style compiler that we have in the production, right? And we would like to be able to apply search for both graph and subgraph levels, and also have flexibility to configure what kind of optimization passes we want to tune, and then leverage the heuristic for the rest for our scalability. So that's the goal of the project. And we are targeting XLA TPU compiler because this is the compiler that we use at Google, and TPU is the most heavily used accelerator for machine learning at Google. And to remind you, XLA is essentially the back-end compiler for various machine learning framework, including PyTorch, TensorFlow, JAX, and so on. And this is some of the optimizations that happen in the XLA compiler. And these are just some subset, but these are like the important ones that I would like to highlight. So here on the first block, I show you the graph level optimizations that happen in XLA. So this include graph transformation, algebraic simplification, layout assignment. And the reason you want to do a layout assignment at the graph level, because when you make a decision for some specific node, the other nodes in the graph, usually nearby node, is affected a lot by that decision. But there's also like long range dependency decision as well, right? So that's why like layout assignment, you probably want to look this at more or less at the global scope of the program. And there are other things like operator fusion, like which nodes you want to fuse together, rematerialization.
Can I ask a question here?
Yep.
I've actually been thinking about various layout optimizations a bit, and don't have enough kind of industrial context on this. Do you to the extent you can talk about it, how much variation is possible in layouts as data layouts flow through a program? Like I've always wondered, are layouts changing frequently through a program, or do you usually just pick, an activation and await layout and you stick with that through the whole program? Is there a wide space of transformations in the layout space?
Yeah, so I think it also depends on the hardware target you have, right? I think some of the hardware target, it's not flexible. So for those, you don't have that many options. I think for GPU is very flexible, but the limitation is coming from cuDNN. Like if you want to use cuDNN kernel, they only support like fixed format for the layout, right? I think for convolution, they support like 2 kinds of layout or something like that. So if you rely on like library kernels, you also like restricted in that case. But if you build your own code generation, you might have more flexibility. For TPU have a lot of flexibility for the layout options for different ops. So that's why it's a very interesting problem. In terms of like where the layout change happen, I think it's usually the case that you want to minimize layout changes, right? Because layout changes consume time, right? It takes time to do layout changes, but it could be beneficial because when you change, the later part can be much more efficient using that layout. So it's a trade-off, right? But in most cases, you kind of try to want to minimize the layout changes, but sometimes layout change can really helps because the later computation is much more efficient. So it's a trade-off. Yeah.
I see. Thank you.
Mangpo, sorry, just right here, another quick question. So looking at these optimizations, which clearly have like potentially a lot of interdependencies, I feel like you're setting us up to expect that this problem is impossible, in the sense that I want to both sort of optimally take into account the effects of earlier stages on later stages, but I also want to keep it pass-based and modular, right? Like one's like pass, and I want to separate these things. And so like in my mind, like this is the tension, right? Am I anticipating the right kind of like, this is like, these are the challenges, like how do we have both? Is that?
Yeah, exactly, right?
Okay.
Because if you look at production compiler, right? This is the way that people build production compiler. You have to separate these into multiple passes, otherwise it's not going to scale. Like you're not going to be able to compile program within a minute if you don't separate these things, right? So that's why production compiler is built this way. But then it's hard to do search in this space because these things are separated. And if you search for only one pass at a time, you kind of like stuck with that local optimization, right? So like how you enable like joint optimization of these things together, it's a very challenging problem, especially in production compiler when you have paths that organize in this way, right? And yeah, so that's what I'm going to be talking about. Yep. Right. And then there are also optimizations at subgraph or kernel level. And these are usually the optimization that you can make a local decision within that kernel or subgraph, and it does not depend on other subgraph, right? So for example, subgraph or kernel that I talked about in this particular context is then when you already make all these graph level optimization, especially like fusion decision, you make a decision that you're going to fuse some of the nodes together. So those are, the box that kind of like group the smaller nodes together. That is the fusion node. And a fusion node is basically like one kernel or like one nested loop. So within one nested loop or one kernel, then there are local optimization problems that you can decide for that particular kernel. And one thing to notice is that for most of the accelerator, they usually execute one kernel at a time. So meaning that, these are not executed in concurrent. So that's why the decision made in one kernel is optimal for that. Okay, so those are some of the important optimizations that I would like to mention. And here's the overview of the XLA TPU autotuner that we built. We call it STAT as a short name. So on the left-hand side, I show you again the graph optimization and kernel level optimizations that we are looking at. The ones highlighted in blue are the one that we support auto-tuning at the moment. We plan to support more in the future. And the yellow box in this picture are the components that we apply machine learning to accelerate the auto-tuning process. So let's take a look at the fundamental part on how we expose these optimizations as search problems. So we first look at one optimization problem at a time because it's simpler, right? So we define a path configuration for a tensor computation graph on a particular optimization path as a collection of per node configurations that will control how we transform the graph. So let's take a look at an example for layout assignment paths. So layout assignment paths have the responsibility to assign physical layout for each of the tensor in the graph, or like the input output to the node. So in this picture, I highlight in blue each node is annotated with node configuration, which represent the physical layout of input and output of the node. And in this particular configuration, the output of add have different layout than the input to convolution. So with this, the compiler or the layout assignment path will have to then insert the copy operation or the transpose operation to fix the physical layout to be according to the configuration, right? So typically in the heuristic, basically the heuristic come up with the annotation, right? But here we're gonna search for these physical annotation. And there are multiple ways to define search spaces for layout assignment. Naively, we can consider layout options for each input-output tensor independently of other tensor in the graph. Just consider all permutation of its dimension, right? But this can lead to a lot of invalid configuration because there are constraints imposed by the compiler or the hardware across nodes and tensors. So instead of go with this option 1, we go with option 2, which is a much more compact space where we only tune the layout options for important ops for this particular optimization, which include convolutions and reshapes. And for each of these op, we then query the compiler for the valid input-output layout combination. So we make sure that we don't violate the constraint. And once we make decision for these important ops, we then leverage the compiler layout propagation algorithm that will propagate the layout from these ops to other ops in the graph. So with this formulation, we guarantee that all the candidates in the search space are valid. So that's a good thing. And here is the results on auto-tuning using these different two search spaces and the speed up that we get from auto-tuning. And you can see that clearly using the proposed search space that is much more compact, it's a lot better than the naive search space. Next, we also support auto-tuning operator fusion. So operator fusion optimization is basically looking to fuse some of the nodes together. The benefit of fusion is that when you fuse things, the intermediate result doesn't need to be saved in the slow global memory, right? You can actually use the intermediate tensor by the consuming ops right away. So it reduces the memory usage, reduce memory traffic, but it can incur recomputation. So in this figure, when we fuse add to copy and reshape, add needs to be duplicated. So we have to pay this recomputation price. So it's a non-trivial optimization trade-off. So instead of relying on heuristic, we essentially assign a fusion configuration bit to each node in the graph, and one bit equal to 1 means that we have to fuse that node with all of its consumer, and 0 means we do not fuse the node with its consumer. So this is how we expose fusion search space. That's formulation number 1. Alternatively, instead of doing this per node configuration, you can also do per edge configuration bit. So in this way, you actually have more control, right? But the search space is bigger. So there's a trade-off there. The other thing we consider is to assign node priority value instead of controlling its fusion behavior explicitly. This is more because this formulation, it's easier to integrate with the current heuristics because the current heuristic maintain this node priority and like fuse according to the priority of the node. So it's just like easier to integrate with the existing heuristic. So we also explore that option. And then the last one is instead of tuning the fusion per node or per edge configuration, we're gonna tune flags instead, where the flags are the parameters for the heuristic. So there might be like some magic number that used in the heuristic, or like some hard like condition. So we can like tune those flags to parameterize the heuristic. The good thing about this option is that the search space is much smaller, right? Because it does not depend on the number of nodes or edges in the graph, but it's not as expressive. And this is the result comparing these 4 search spaces. And the per node configuration is the best, pretty similar to per edge. Per edge is a little bit worse, and probably because the search space is bigger, where the node priority and flags are clearly worse than the other 2. Okay, so
can I ask first, is there so this is the speed up of the compiled program. How about a comparison of like how well these approaches perform compared to each other? Are they all like within some kind of tolerance for compilation or search time, and that's basically all you need to do?
These experiments, we use the same number of tuning workers, so 10, and then we run them using the same time budget.
Okay.
And then this is like the best speed up that they found.
I see. Very cool.
Given the limited time budget.
Why do you think node priority is so poor? Is node priority specific to is it like prioritizing which things would be most important to fuse, or is it something more general?
Yeah. So it prioritizes like which node is the potentially most beneficial to fuse. The reason why it's so bad is because, again, I didn't mention this. So for all these, we search the search start from the default configuration, where the default configuration should represent the configuration from the heuristics, right? Turns out that for the node priority, we cannot faithfully represent the default behavior in this space, and it is because when you fuse things, the priority could change. Essentially, like when you fuse 2 nodes together, the priority in practice it will change in the compiler, because the compiler look at the fuse node and like recompute the priority value. But in our search space, we do not dynamically change the priority value of the fuse node, right?
I see. Okay.
It's like really hard to express that upfront. And because of that, we cannot faithfully represent the default behavior in this space.
Yes. Okay.
Yeah.
Okay. Okay. Sorry, I'll stop interrupting.
No worries. Okay. All right. So.
Can I have a question?
Sounds like Ziha has a question.
Yep. My question.
Oh yeah. I mean, so the operator fusion strategy proposed in your paper is not a sequential process, right? It's you only assign values and set properties, and the search process is globally, not sequential.
Yeah, that's right. Yep. So we made the decision for all the nodes all together.
Yeah, the Tensor paper mentioned that sequential search process may find some local optimal solutions.
Because you can, if you do sequential in a way that you don't do backtracking, right?
Yeah.
Then it could stuck in the local. Yeah. I think the reason we don't do it sequentially, it's also like really expensive to evaluate all the intermediate steps, right?
Okay.
Because we see like 10,000 nodes. Like that's like the typical model we see in Google Fleet. And then if you make one decision and you evaluate at a time, right, you would have to evaluate like 10,000 intermediate steps. That's like for one full candidate, right? Like then you like exceed all the time budget for tuning.
I see.
Yeah.
So this also do not cover all the possible fusion strategies in Tensor. This only covers say how do we transform the dimensions, something like that.
So the fusion that we are looking at, it's this kind of fusion where you fuse two, or like, you fuse consuming Oh yeah, sorry. The fusion that Tazo did is more like you do concatenation.
Yes.
So what Tazo does is that if you have like two matmul, for example, and they share the same input, right? What you do is that you concat the second operand together and do only one matmul. So you combine like two matmul into one and using concat instead, right? So that's a different kind of fusion. We don't call it operator fusion in XLA. That one is happening in the graph transformation or like algebraic simplification pass.
Okay, so this is only
which
about
we haven't tuned that yet.
Reorder and fusion, so consecutive operators. Like the right.
Yeah, so the fusion that we are looking at are kind of like looking at these like parent, like
Okay.
producer consumer kind of fusion. Mm-hmm.
Thank you. Just go ahead.
Can I add another question?
Yeah.
So the strategy you propose, I was just wondering, can you like mix the strategy, like you mix like node and then mix for edge fusion? Is that possible?
I think it's possible. We haven't tried that, right? Like one idea would be maybe you like start with the coarse grain search space first, because you like kind of like mutate at a bigger step, and then once you kind of like get to a pretty good solution, then you can like do the fine grain, the search space that have more candidates, right? So I think that could be done too, but we haven't tried that.
I see. Thank you.
Yeah. Okay. All right. And so apart from the graph level optimization, we also look at a few kernel or subgraph level optimization, essentially tuning tile size selection. So these are very common parameters that most of the machine learning search compiler tune. So we tune tile size and also some of the low level code generation flags for each of the kernel. Now comes to the most tricky part, right? Like how can we then orchestrate tuning different optimizations jointly together? So for the simplification of the explanation, let's consider just two optimization, A and B, where let's say A is layout and B is fusion. And when we look at this, right, the configuration for pass A, called config A, determine the input graph to pass B or GB. So let's take a look at example, right? Here, if we have a particular layout assignment highlighted in red, we're going to get a particular input graph to the fusion pass in the middle. If we change the layout just slightly, the input graph to fusion is now no longer the same, meaning that the configuration that we used to have for fusion is no longer valid for the new graph in this particular case, because it does not contain the configuration for the copy node, right? So the naive way to work around this is that every time we change configuration A, we can start the search for B from scratch, right? But that's kind of terrible. That's very inefficient. So instead of doing that, we develop a generic methodology for joint auto-tuning multipass compiler by iteratively executing this particular search step, where the first part of the search step basically just pick which optimization to tune. So to obtain joint auto-tuning behavior, we can alternate between tuning different passes. So then the next step is to generate candidates. So in each round, we maintain a set of candidates. For each candidate, we keep track of all the intermediate graphs at different stages of the compiler and all the configurations of the pass that we are tuning. And the generate candidate will then mutate the configuration for the optimization that we choose in that route. So in this case, let's say we choose A, so it's going to mutate config A to config A prime. As I showed in the previous slide, when we do this, config B is usually no longer valid. So we have another function that will fix the candidate to be well-formed. And the gist of this function is essentially to update the subsequent graphs, right, after the pass that we change the configuration. So when we change config A to A prime, we have to update like graph to B and everything else after that. And we also need to update config B to be well-formed or compatible in particular, config B prime, the new config, must have all the configuration of the nodes that show up in the new graph GB prime, right? So how do we get these configurations? Well, first, we can look at the old configuration and see if the nodes in GB prime exist in the old configuration config B, we would just use that configuration. But if the node does not exist in config B, then we're going to console a global configuration store, which is a data storage that maintains the best configuration so far for all the nodes we have seen in the search process. And if the node does not appear in config B or also not in the global configuration store, we will then use the default configuration, which can be randomly initialized or extract from the default heuristic solution. Now, I talked about this global configuration store, so let's expand on that a little bit more. So it's a very simple data structure. It's a key value store where the key is the fingerprint of the node and the value is the configuration of the node. And we update this configuration store every time, not every time, every time when we evaluate a candidate. And if the candidate is the best candidate we have seen so far, we will then update the store according to that particular candidate and have the entry per the node that appear in that particular graph. One thing to notice is that this fingerprint of the node, the fingerprint of the node capture not just the node itself, but also the context around the node, right? And this is because the optimality of the configuration of the node does not depend on just that tensor operation, but also the subgraph around it, right? And the size of the subgraph or the neighborhood size, this is something that we do the hyperparameter tuning that fit well for that particular optimization. Okay, so basically that's the gist of how we enable joint auto-tuning multiple passes in the compiler. So at the end, we have the final search schedule for the XLA compiler where we make a decision to separate tuning graph level and kernel level separately for scalability. We experiment joint tuning, layout, and fusion together, and it seems to do better than tuning layout and then tuning fusion. However, when we try to tune tile size and low-level flag parameters, they are worse than tuning them sequentially, and this is probably because the search space explosion. So our final schedule is to first tune layout and fusion jointly, followed by tile size tuning, and then the flag tuning. And here is the results of our experiments that run the XLA Autotuner on 150 machine learning models, both training and inference. And these are graphs either from production or research usage across Google. And this chart shows the model that achieved 5% or more speedup. So in summary, in the best case, we found up to 2.4 speedup on one of the model, and about 13% of the model achieved 10% or more speedup. And if you look at the breakdown of the speedup, it seems like most of the benefit is coming from fusion and layout auto-tuning, whereas more number of benchmarks seems to benefit from tile size selection. Okay, so that is about how we expose search space and how we tune things jointly. And I'm gonna, because we don't have much time left, I'm gonna quickly go through the rest on how we apply machine learning to reduce the auto-tuning time. And so the first part is we apply machine learning to build a learned cost model, and then use this model to evaluate the candidate instead of relying on hardware, which is much more expensive. And this is the work that is done by Sam and me, and Sam is also at UW. He was interning with me a few years ago. So the idea is that when we have the graph, we can compose the graph into kernel. Once we have the kernel, we can then use the learned cost model to then predict the runtime of the kernel. And the high-level idea of our cost model is using neural network. In particular, we use graph neural network because kernel or subgraph is naturally represented as graph, right? So it seems to fit well with the graph neural network model. I'm not going to go into too much details. We use different kinds of losses to train the model. to predict absolute runtime, we use mean square error. For the task that we want to predict relative runtime, we use pairwise rank loss. I'm gonna skip this part and go into, okay, this one is kind of interesting. So in this work, we do a little bit of ablation study, and these are the interesting thing we found. So we discovered that for the task that we only care about relative runtime, for example, predicting which tile size is the most optimal given a particular kernel, we found that using rank loss is very beneficial because it showed to like reduce the percentage error by like 10 percentage point, which is pretty huge. We found a rather simple model like GraphSage to outperform more complex model like graph attention network and other sequence model like LSTM and transformer. And the other one, we comparing using a very simple reduction model versus more complex model like LSTM and transformer, and found that the performance are quite comparable. There's a little bit of gain that use more complex model, but not a lot more. So it seems that most of the benefit is actually coming from the graph neural network for our tests. And
can I ask?
Yeah.
I guess I'm like, what's an example of a task that you need an actual prediction of absolute runtime versus rank?
Yeah, right. So for our use case, when we tune fusion or like layout assignment configuration, those we actually need, the way this thing work, right? This particular cost model make a prediction at the kernel level. So let's say you have an arbitrary fusion configuration. What we do is that we compile the graph using that fusion configuration and then get the kernel, right? Yeah. Once we have the kernel, we can then use this cost model to predict the runtime. So for this, we have to predict the absolute runtime, and then we compute the summation to get the total runtime of the graph.
I see, okay.
The other way that we could do this is that predict the runtime at the graph level instead of the kernel level. So you can say, given a graph, given a fusion configuration, predict the runtime. Yeah. That like predict the whole runtime of the graph, right? That you can predict relative runtime, but it is much more, it's like extremely difficult to do this at the graph level because the graph is huge, right? Like 10,000 nodes.
Are you sticking any, like how big of a subgraph are you putting into inference in this?
Yeah,
in this model?
So the subgraph, I think on average, we've seen about 100 nodes.
Okay, okay.
Yeah, that's like the average size we see.
I see.
Okay. Actually, maybe it's smaller than that. Maybe like 10 to 100. Yeah.
Okay.
How do you partition the large graph into the small subgraphs?
Yeah, so we partition it according to the fusion decision, right? Because our notion of kernel is basically one fuse op.
Okay.
So in the original graph, all the primitive ops are not fused. After the fusion pass, some nodes are fused together, and that basically form one kernel.
Yeah.
Make sense?
Makes sense, but you say the original graph may have thousands of nodes, but the model is supplied at hundreds of nodes. So that's a change of, I mean, does a fusion reduce the number of nodes?
So it's like this, right? Maybe this is not a good picture. So maybe the other one is a better picture. So let's see here. Yeah, I think I have. That's for fusion. Yeah. Okay. So let's say that this is the original graph, right?
Yeah.
And then you fuse some of the nodes together. So basically, this become one fuse op or one kernel, and this is another op, another kernel. So when we use the learned cost model, we use the learned cost model for one kernel at a time.
Okay,
right?
okay, I see. That makes sense.
So the subgraph for the kernel is much smaller than the entire original graph.
Cost model only happens when you try to fuse kernels, so you only need to
right,
incorporate
exactly.
Okay, that
Right.
makes sense.
And as I discussed earlier, that it's possible that we can apply the learned cost model at this level too, like take the entire graph and like a fusion configuration, a layout configuration, and predict the runtime. But it is extremely difficult. I have tried. It is an ongoing project. I'm saying that I haven't seen a really good result yet, so I'm not presenting about that today.
What about something like okay, so if you have if you're trying to compare two different fusion strategies, and I don't know how different those often look, but something you could do is basically like diff the two graphs and basically compare only the kernels that are different. Yeah, because then you don't need to sum the whole runtime. Would that be possible, or are they just too different? Are the layout strategies often they're just too different that you'd have too many things to compare?
Actually, I think for layout, it could be different, but for fusion, if you change just only a few fusion bits in the configuration, most of the kernels would be the same. So I think we also implement like a caching mechanism where like, if we have seen this kernel before, we just use the cache value.
Yeah.
So basically what would happen is that you have like two graphs with similar fusion configuration, and then you like generate the kernel. Most of the kernel will be the same, and only a few kernel will be different. So we only need to measure those kernels.
Yes.
Like if we have to measure that on hardware, or like only run the inference model on those diff kernel.
Okay. Yeah, and I sorry, I said layout when I meant fusion, but yeah, I was talking about fusion.
Yeah.
Sorry, I have another question. Yeah, you say you use something like transformers or graph neural networks, but what are the node features? Does that mean you have per operator per feature, something like that?
So we have the node features. So for each of the ops, like we can extract the node feature from it. So these are things like tensor shape, convolution size, padding, striding, and so on, right? That is associated with node, and also the opcode. And we use like opcode embedding. Yeah. So like the types of the operator.
Yeah, convolution and matrix multiplication have different opcodes, and you use different embedded, something like that.
Right. Yeah, exactly.
Good.
Right. And like you get node embeddings as an output from the graph neural network. And then we have reduction model that then get kind of like a summarized kernel embeddings from the node embeddings. Yeah.
That makes sense.
Is this all trained end to end, or is there like for example, for opcodes, do you have some kind of pre-training to generate those embeddings?
So we train everything end to end, but we have some experiments on transfer learning where we train everything end to end on, for example, like type size selection. And then we like fine tune just the last part for flag selection. So we have done some of that experiment, and it seems that the transfer learning seems to help. Yeah.
Oh, that's cool. Very cool.
Yeah. Okay. So with
Can
that,
I also?
Yeah, more questions.
Yeah, more questions. It's a very interesting topic. So, so you train the graph neural network for the cost model, like for all the different machine learning models, and then they can predict well, or do you need to like have different category, like, oh, okay, this is feature model, so I train the cost model for the feature model, and this is maybe a transformer model, like language model, and you use another like cost graph neural network train for that, or they work for all?
They work for all. At least at the kernel level cost model, they seem to generalize pretty well. But as I mentioned, the ongoing work that we're looking at the cost model at the graph level, we kind of see that using one model for all doesn't seem to work. So for that, we might have to have like a different experts for different kind of models.
Yeah, I feel like like CNN has a lot of conf up, I would guess, and then transformer has different set of operator. Maybe I don't know. Yeah. So that's what I'm thinking.
Right, at the kernel level, it seems to work really well, because I think, like when things are composed into like a much smaller subgraph, and if you've seen enough diverse subgraph, then your
Mhm.
model kind of learn for everything.
Yeah.
Mhm.
Makes sense.
Okay.
Yeah, thank you.
All right, and this is the results on when we apply the learned cost model on the auto tuning. So what we do is that we basically replace the normal evaluation process using the learned cost model. And then at the very end, we select the top K candidate according to the cost model to run on the hardware and measure and select the best from that. So comparing with the strategy of using learned cost model and pick the top K, compared to run everything on hardware, which is the shaded bars. So we are very comparable, right? Like we can achieve almost the same speed up as using the real hardware. And in terms of the tuning time, we actually reduce the tuning time significantly, especially if you ignore this light blue bar. So the light blue bar is actually the part that we can actually run this thing entirely on CPU, right? Because it's the search process and use the learned cost model. So if you only consider the time we need the actual hardware, the actual accelerator, it is the solid color part, which is much, much smaller. And we cared about this a lot because the TPU is like on really high demand. So we want to minimize the time we actually need to use TPU. Okay, so let's move on to another part that we apply machine learning. This is going to be pretty quick. So we explore different search strategy. Simple one like exhaustive search, similar annealing, evolutionary search, and also machine learning based search like model-based optimization and deep reinforcement learning. I'm going to skip the detail and go to the result. And to our surprise, simple search technique like similar annealing and evolutionary search seems to reliably do better than RL and MBO. We hypothesize that this is because the very high dimensional search space makes it really hard to fit an accurate model at the graph level for RL and MBO. Note that for RL and MBO, we train the model from scratch for each of the benchmark. It is possible that pre-training could help them perform better, but we have not do like an extensive experiments on that. And here is one example trajectory of speed up over time. And you can see again, SA and Evo is doing pretty well, and RL apparently also have really high variance. So it's just like a lesson learned that it's not that all machine learning is better than the simple search techniques, right? So these are really highly dependent on the problem, and you have to try and see which one is the best, and don't jump into like using like complex machine learning right away. So that it's about all the components we have in the accelerated TPU autotuner. And I want to also emphasize that we developed this, but also actually deploy this at Google data centers. So because we don't have enough time, I'm going to jump into our solution. So what we do is that every day we have Google-wide profile information that can collect the top workloads that run in TPU fleet. So we feed that information and run the offline autotuner on those top workloads. Then we save the best tune configuration into the code base using version control to basically guarantee reproducibility. We also have a monitoring system that keep track of how much benefit we gain from auto-tuning these fleet workloads, and also to detect anomaly. And this is because, like the auto-tuning process still takes time, so we cannot put that as part of online auto-tuning as part of the compiler. And we also don't want the user to, have to run like offline auto-tuning themselves, because we try that and, users are just, they're very sticky. They don't want to change anything in their workflow. So we think that this automated process is the best way to deploy the autotuner. So we have been deploying this about a year now for type size and flag selection at the kernel level. And it has been tuning more than half of TPU fleet every day. We actually deploy the learned cost model in this process as well. And the cost model enable us to tune 20 times more kernels per day. And we have been saving more than 1% of total TPU consumption at Google. In terms of saving versus tuning ratio, we spend about 1 TPU to save more than 10 TPUs worth of compute. And yeah, if you're interested in more details, here are some of the publications that we recently published at PAC, which is more about the search formulation and the joint tuning, and then the learn cost model at MLSys conference. And yeah, I like to end with this slide, which is all the collaborators I have on this project. Some are at Google and some are our interns. And yeah, with that, I'm happy to take more questions.
Give Mangpo a big round of applause. Thank you. Mangpo, that was an awesome talk. Obviously, you've got a lot of questions. There's a lot of excitement here for this kind of thing. I wanted to ask a really quick question. At the beginning, you mentioned that, researchers use small models in their papers to do their evaluation. And obviously, Google has access to much larger models. What do you think researchers can do to actually use more realistic models? Is it basically just like, okay, go grab BERT, and if your thing doesn't work on BERT, you should make it work on BERT? Like, how do we solve this problem of we're not using realistic models?
That's definitely one of the first thing that researchers should do, like look at the big model and make sure it works there as well. And also like think about both inference and training, right? I think a lot of research tend to focus on inference, and I think there's benefit on that because obviously if you can like make inference go faster, that's definitely beneficial, especially for like model serving. But there's actually a lot of workloads that, training require a lot of time. So saving training is also very important as well. And lots of these compiler for machine learning that I've seen in research, they tend to focus a lot more on inference, and that's because the graph is much smaller, right? If you look at training graph, it is like 3 or 4 times bigger than inference. So that's another thing that you could look at too, not just inference, but also training. Another observation that I have is that a lot of library kernels like MKL or like cuDNN, they tend to optimize better for training. So when you like compare on inference, you might get like much better speed up compared to those kernel. Whereas then when you start comparing on training workload, the benefit is not as high anymore. So that's another thing to look at.
Mangpo, how are they more optimized for training? They're just more data parallel, like?
Yeah, more data parallel, the batch size tend to be bigger, right? And it seems that they can like utilize better the hardware. And I don't know, for some reason I think there's like one paper that came out at PLDI this year where they evaluate the approach both on inference and training. And when you look at the inference gap, they are like much better than like cuDNN. But then you look at training, they are like 10% better. Like inference is like 2 times or something like that. Right. So it's like a very different gap there. Mm-hmm.
Hey, Mangpo. I had a question on the cost modeling. Are you guys primarily cost modeling performance when you're evaluating this? And if so, are you looking more at latency performance or bandwidth performance? What?
Yeah, we primarily looking at a performance. In particular, we look at latency. So we basically measure the times that it takes to run that particular model. Yeah.
Has there been any interest in things such as energy, or you had even mentioned that the the demand for the TPU is quite high. I was kind of thinking cost modeling something almost like the cost per inference with a heterogeneous system where you have a CPU and a TPU. You could actually get really crazy with your cost modeling and do a cost where like maybe it makes sense to do some of the really dense matrix on the TPU, but activations on a CPU where it's a lot less costly, a couple cents to do those sort of activation functions.
Yeah, I think that's a very good question. And as far as I know, people have not looked into this space, especially optimizing for energy in basically like using heterogeneous system. I think a lot of work, it's kind of focus on like one of the device, right? Like make like the model run as fast as possible on like CPU or GPU or TPU in separate. But I think that's a very good good question, because in the end, we have to look at the holistic system, right? And like, what can we do there? Yeah, so I think it's a very interesting direction.
Maybe on that front, I know that we're running out of time. Sorry, Mangpo. Thanks for being so generous with us. Super appreciate it. But I think like this question about portability and different cost functions is super interesting, right? Like if I train the model on TPU, but then I want to go run it on some other device that maybe doesn't have bflow 16 or something, right? Like I think there's this very interesting angle of heterogeneity, right? Like in your context, I mean, in some sense, like your team controls this whole stack, right? Like the compilers, the model, like the models, the compilers, the hardware, like the whole thing. And so there you can really focus it, and the data center, like all of it, the scheduling. But now, you know, if you want to deploy it to like a bunch of different versions of phones with different accelerators and a bunch of different laptops with different accelerators, I feel like the trade-offs start to get very subtle and confusing. I don't know if you've like thought about how you would, like how extensible is this pipeline? Like, can I plug in more backends and have it work across all of them? Or I don't know if people have even tried that yet.
Yeah, you know, in theory, I hope it works, but a lot of these in practice, it's hard to do because compiler tend to specialize for, you know, different hardware. Like even though like fusion or layout assignment, they are like a general optimization, like it should apply to other hardware as well. But like if you look at the heuristic, it still tend to like, oh, it only works for TPU because it have these hard-coded things inside the algorithm. But I would hope that, you know, the way that we expose the search space is generic enough that for other backend, it should be reusable as well. So that's the hope. We also talked to, you know, like the mobile team, that they actually have a different compiler backend that it's not using XLA. So they, it's called Erie, which is an open source MLIR compiler for mobile backend. And yeah, I've been talking to them on like how to apply auto tuning there as well, especially when they have to target different mobile devices.
Yeah.
Can we like leverage, like learn cost model somehow in a way that, you know, like we have a pretty good learn generic cost model and then just apply kind of like fine tuning for each of the different device to make it like fit for the device well. But
I really like
it's like very early stage. Yeah.
I think this like model tuning, like the model shows up to some hardware that's available. How do you automate? I think I love that direction. I think it's super interesting. Also have to run. Mangpo, thank you so much. It was so good to see you. Hope that we can catch up in person soon as well. And thanks everybody else. See everybody soon.
Yes, let's give Mangpo one last round of applause and thank her for joining us and taking extra time with us. Thank you so much, Mangpo.
No problem. Thank you for the invitation.
Of course.
It's nice to see familiar faces again.
Good to see you, even if virtually. All right, everybody. Thank you for showing up. Thanks for being such a good audience.
All right.
Bye, everybody.
Bye.